Hello everyone. So this is the first video in a series of videos that I'm making to help you guys understand the foundations of the Solo model, which is not very straightforward concept in macroeconomics. So I'm hoping that these next videos would serve as a very helpful guide to help you guys understand basically the foundations and principles of the Solo model, as well as the basic principles of macroeconomics. So going into this, we're diving into something called the Cobb-Douglas production function. This is one of the most fundamental concepts in macroeconomics because it deals with the concept of aggregate production. So first, before we get into the Cobb-Douglas function, let's kind of go over the inputs of what is generating our production function. So just loosely defining some things, let's just review what are the type of inputs that we have in our economy. So one of the very first inputs that we have is looking at capital. So we have capital. We also have human capital, which is basically looking at knowledge and such. Other things we have inside here as well is looking at labor and natural resources. So listing just several of these things, there's other sources of capital. There's education, which is part of human capital. There's also knowledge, which also falls under human capital. But generally, all these things are classified under something we call inputs. So inputs are generally, as they suggest, things that we enter into our production function to generate output. So when we look at output, we have some things that are classified as output. We look at GDP, which is gross domestic product, as well as income. And we also have goods and services. So all of these things fall under the category of output, essentially. Okay. So next over here, we want to kind of generalize this in a mathematical formula, or as our production function. So we generalize this mathematical formula by saying, we're calling these output as y. And we have our output, we have a function of our inputs. So for example, we have capital and labor. I'm just using the two most basic inputs when it comes to our production function. So this is simply just saying that the output is a function of inputs. So when inputs are generated, or when they're put inside our production function, so our production function is essentially f. This is our production. And then we have these things, of course. We have our inputs. And then we have this, which is our outputs. So essentially, we have the inputs going to our production function, which generates our output, which is measured in terms of GDP, income, goods, and services. Okay? Now, that's an easy mathematical way of writing that. But what if we are also to sort of add some other things into here? So another thing that we can also add into here, we can also add A, which this is referring to technology. So technology is essentially looking at things that increase sort of the productivity or sort of the efficiency of these inputs. So you can think of these raw inputs as capital and labor. So examples of capital is looking at machinery, factories, land, all these sort of things. So if you have this sort of capital and labor, which represents people and such, technology and such are things that sort of augment, or how we say, increase the efficiency of these of these inputs. So they make these inputs more productive into our function, which we'll categorize mathematically later on. So now where enters the Cobb-Douglas production function is here. So very identical, except for now we're going to break everything down. So our Cobb-Douglas production function is our inputs, which is we're denoting as y, multiplied by our technology. And over here we have capital, and I have this little a over here. I'll explain what that is. Multiply by L, so that's capital labor, and then we have 1 minus A. So probably thinking, what is A exactly? Well, A is basically equal to a parameter. A parameter is essentially just a number. And A is a number that is set between 0 and 1. Sorry, I should put this in brackets. So it's a value that takes on including 0 and minimum 0, maximum at 1. So what does this necessarily mean? So essentially what this means that if I were to say, for example, if A is equal to 1/2, then what basically we have is y multiplied by A, well, capital A, technology, times capital and labor. So what if A is equal to 1/2, what it basically says is that our production function, our input, our outputs that are being generated, half of that is explained by capital and half of that is explained by labor. So typically, as in a textbook, as what they mentioned, is that A is normally equal to about, let's say, 1/3 or something. So essentially we have 1/3 of capital and 2/3 of labor that are used to kind of predict output. So this is saying 50% of what is being of what's generating services and GDP and income and such. 50 of that would be capital, 50 would be labor in here, assuming that A is equal to 1/2. So this is a parameter, which that is a number that we just assigned over here. Okay? All right. So let me move on to the next page. Okay. Now, for over here, now when we're looking into our production function, I was talking about this whole concept of productivity. So essentially, what does this necessarily mean? When we're looking in terms of productivity, we're referring to productivity of inputs. So let's keep our model simple using just the two most simple inputs that are used to measure productivity, which is capital and labor. So I'm going to define something that's called marginal product of labor. Let's use labor first. So what marginal product of labor is basically, it's saying that when we're testing to see how effective labor is in generating our output. So this is just review from Econ 130 and Econ 131, where we look at to see the change, which is represented by this triangle, the change in output over the change of labor. So what this basically saying is that when labor increases, at what rate is output increasing by? So another simple way to write this is when you look at yt plus 1 minus yt over lt plus 1 minus lt, where t plus 1 is the future, t is current. So we're looking at our difference between in the future versus now, and then taking the ratio of these two things. So graphically, what this kind of shows is that when we're measuring this on our y-axis Cartesian plane, we have our output over here, for instance, and we have our labor. So for example, there are different sort of productivities that we can observe over here. Now, if we ever have a line that's completely straight over here, then we say that this is constant, that is constantly growing, that it's proportional. So the rate at which L is growing the rate at which y is growing as a result to having an additional input or additional labor is always constant. So this, for example, could mean that as labor always increases by 1, this will always increase by the same amount no matter what. There's another one where we have this over here. So here I'll put constant, for instance. This is constant marginal product of labor. This is over here. This is something what we call increasing or rising marginal product of labor, where this is saying that with more labor, our output is actually going at an increasing rate. It's just exponentially. I mean, it's just growing exponentially. So as you can see, for any of those who are math majors, this would be an e of x function, looking at this sort of exponential growth. So it's not unusual for economies to actually observe this or sort of have this, but this basically just means that when you hire more and more labor, you're more productive, which generally gives higher output. Now, what we mostly observe in typical economies, and what is very important when we look at the Solow model, is this. This is, for you guys who are math majors, this is an ln of x function, natural log function. So this would be something called diminishing marginal product of labor, which is the most important one, or the one we're going to be working with the most. So what this basically says is that with each additional labor, this output is decreasing over time. So this illustrates the problem of what's called too many cooks in the kitchen. So what this basically means is that whenever you have one chef cooking, they normally can produce a lot of food, but when you have more and more people cooking in the kitchen, it gets overcrowded, and generally output is becoming counterproductive. It's being less efficient. So this is our diminishing marginal product of labor. So this is all review, by the way. Okay? Now, the same thing could be said for marginal product of capital. So if you want to look at marginal product of capital, just change everything just from L to K, and it's the same thing. It's symmetric, same exact thing. Now, basically, when we're looking in terms of calculating or finding what if a function is exhibiting increasing marginal productivity, decreasing, or such. So generally, what this basically means is that how we measure this, so let's just draw a line over here. How we measure this is that suppose we have our current output is yt, our future output is yt plus 1. Now, let's just define a few things. If yt plus 1 is equal to a, which is technology, multiplied by y of t, then we see that this is constant. So what this basically saying is that with our technology inputs, or with our technology adjusting, we can see that our input back then is the same as now. So it's still growing at a constant rate. Now, if we observe that so this is constant, by the way. Now, if we observe if our future output is greater, then we're having increasing productivity, or it's increasing returns to scale. And here, this is decreasing returns to scale. So we're observing decreasing productivity, essentially. Okay, so I guess to go over some mathematical examples of how to solve for this. Let's dive into one example. I'm going to pick an example from the slides. Just very, very simple. So for example, if we have our production function of f of k of L, and this is equal to, for example, KL, or square root of k times L, then what we can necessarily do is that we can apply a scalar, or we can just apply a parameter. And you can call this Z, B, A, B, C, D, E, F, G, whatever you want to call it. So let's just call this Z, for instance. So we're applying just a number, a scalar, or a letter, sorry. So apply scalar, and then we're having essentially Z squared times K times L. Okay, so we're applying it, we got this Z squared because this originally came from just applying z times k and then z times L. So this became z squared, by the way. So we're applying the scalar to each of the inputs. Okay? Now, essentially, what we can do over here, this is just very simple. The square root of z squared is it's essentially z times kl, or square root of kl. And over here, we see that over here, that if we apply z times a square root of kl, now the thing about it is that keep in mind that this kl is equal to f of kl. So essentially we can substitute square root of k of l with this function, and then we get z times f of k of l. Now if z is greater than 0, we can say that there are constant returns to scale. And why are the constant returns to scale? Because essentially, if z is equal to, for example, 1, 2, 3, 4, it's always going to be equal to 1, 2, 3, 4. So essentially, what this means is that it's going to be a constant growth. So whatever we assign z to equal to, this is going to make our function just grow. For example, if z equals to 2, this is going to make sure that our function at every point in time is going to be 2 multiplied by fk of l. So essentially, this is a constant growth. Let's do one more example. So one more example over here. Now, if we had something where we have f k of l is equal to k squared plus l squared over here. Now, for example, let's sort of apply our z value. So apply our scalar z. Now we're applying z. Essentially what this equals to is we're going to have z k squared plus z l squared. And essentially we can separate these things. So we have z multiplied by k squared plus l squared. Okay. Oh, my apologies. Sorry. My apology. It should be this. Sorry. The reason why we apply z over here is we're applying z to the actual function. So it's going to be z times k squared. So we have z k squared, z l squared. So this is, we're going to have a squared value out here because we're just factoring out the z squared. So that was my fault. Sorry. Okay. Now we do the same thing, substitute this with our function, and we're going to have z squared multiplied by f k of l. And essentially, this is an exponential function, which basically means that this will be squared for whatever value, so it's going to be constantly growing. It's an exponential function. So this is going to be increasing returns to scale when z is greater than 1. And the reason why it has to be greater than 1 is because if it's equal to 0, then the whole function just goes to 0. So essentially, this exponential function is making our production function exponentially grow. And if, for example, if this was z, a square root of z, then this would be a decreasing return to scale function. Okay? So, hypothetically, just the bottom line is if you want to learn something like this, if you have something that's, for example, if you had, for example, 1x squared multiplied by fk of l, this would be a decreasing function because we're seeing that when x gets larger, this is decreasing over time, exponentially decreasing over time. If you had something that is square root of x and then fk of l, the root is making the function go smaller and smaller. So essentially, this is going to be a decreasing returns to scale as well. And if you just had something like literally 2x multiplied by fk of l, then this would be a constant, because this is a constant, because this would be a constant with just any value and such. So if you have any more questions, don't be afraid to email me. Otherwise, thank you for tuning into today's lecture. I'll be posting more videos on looking at the solo model because it can be very difficult without understanding the basic foundations of the production function as well as the Cobb-Douglas function and all such. All right, thank you very much and have a good night.